Hello, everyone. My name is Madeline Endres from the University of Michigan, and today I am going to be presenting an analysis of iterative and recursive problem performance. Before we begin, I also want to acknowledge my excellent co-authors, Professors Westley Weimer and Amir Kamil, who were integral to the work I am presenting today. Okay, so to start, let's talk a little bit about the motivation for our research. Iteration and recursion are core concepts in introductory computer science. However, they remain challenging for both students to learn and teachers to teach. For example, in a 2006 survey, CS1 instructors identified recursion and loops as two of the most problematic areas to teach. Part of the problem is that there remains debate in the computer science community over which, if any, programming tasks students find easier when represented recursively or iteratively. As many programming problems can be framed either recursively or iteratively, the question remains which framing should instructors choose when introducing a concept or problem? As an example of this debate, one prior study which specifically compared differences in performance on iteration and recursive framings found that for at least one list based task, student comprehension was significantly higher for the recursive framing. However, for the other non list based task, there was no significant difference between framings, and replications found no performance differences for either task, underscoring the need for future investigation. In our research, we build off previous work to help close this gap. To do so, we present the results of a study with 162 CS undergraduates, in which the same programming problems were presented iteratively to some students and recursively to others. Our study expands on previous work in a few different ways. First, our study is larger in scope. We consider 6 different programming tasks rather than the 1 or 2 analyzed in previous work. Second, we include an analysis of common student errors to give insight into why students may struggle. Finally, we investigate correlations between student performance and background features such as experience, gender, and socioeconomic status. To the best of our knowledge, this is the first work investigating correlations between these background features and performance on iteration and recursion. Okay, so now that I've talked a little bit about our research motivation and overall goal, I'm going to go into a bit more detail about our experimental design. While doing so, I will first cover the overall experimental structure, followed by a discussion of our programming stimuli and our recruitment procedure, as well as our population demographics. To investigate the effects of problem framing as iterative or recursive on student performance, we conducted an online survey of CS undergraduates at the University of Michigan. This survey took around 30 minutes to complete, and it had 3 parts. A programming portion where we gave the students several problems framed either as iteratively or recursively, a spatial reasoning test, and a short demographics questionnaire. I'll now cover each of these 3 parts in more depth. For the programming portion, we showed participants a series of programming problems that were framed either as iteratively or recursively. For each problem, participants had to provide either return value or output of a given function call. These functions were selected randomly from our corpus of CS1 and CS2 level problems. Participants were given 6 to 7 functions with 3 minutes for each one. And in general, participants were not shown both the iterative and recursive version of the same function. Participants also took a short spatial reasoning test. Spatial reasoning is the ability to mentally manipulate objects, and it has been found to correlate positively with programming performance. Spatial reasoning is also a trait that can be improved through training. We were interested in determining the degree to which spatial ability correlated with iterative and recursive program performance, and to measure it, we used the paper folding test, which is a validated standard assessment of mental folding, one of the key components of spatial reasoning. The image on the slide shows a simple example question from the PFT, which asks participants to match the hole punch paper on the left with its correct, unfolded counterpart on the right. The paper folding test has 20 questions and it lasts 6 minutes. Finally, our survey ended with a short demographic questionnaire where we asked questions gauging programming experience, gender, race or ethnicity, and socioeconomic status. For socioeconomic status, we use the Financial Affluence Survey, a validated measure of family affluence. Now that I've given an overview of our experimental structure, I'm next going to dive deeper into our stimuli for the programming portion. Okay, so on this slide I have a table with all of the programming tasks in our stimuli corpus. We chose these particular tasks because they were indicative of common CS1 and CS2 problems, and also because they cover a wide range of input and output scenarios. For example, digit returns an integer representing the sum of the digits of the input number. Palindrome returns a Boolean evaluating if an array is a palindrome, and triangle prints a triangle using asterisks. Of the 7 tasks, 6 had both iterative and recursive framings, while 1, EXP, only had a recursive version. For this talk, we will be primarily focusing on the 6 tasks with both iterative and recursive framings. I also want to draw your attention to the tail recursive column. For some of the tasks, our default single function recursive implementation was not tail recursive. When possible for such programs, we included an additional explicitly tail recursive framing implemented with a helper function. To get a better understanding of the programming tasks, let's look at fib-like, one of the problems with all 3 framings, in a bit more detail. So, fib-like is a task that produces a Fibonacci-like sequence with branching computation. So basically, each number in the sequence is made as some sort of sum of the previous 2. On the screen, I have the iterative framing of fib-like, which contains a loop that iterates based off of the function's input. And now here is the single function recursive framing of the same task, where we can see on the green highlighted line that there are 2 recursive calls to func, emphasizing that this has branching computation and also making it non-tail recursive. And then finally, we have our tail recursive framing of fib-like, which uses a helper function to achieve the same functionality as the other recursive framing and iterative framing in a tail recursive manner. Regardless of framing, here is a template of what the participant would see when asked to solve the fib-like prompt. They would see the function call, func3, an implementation of fib-like, which would have been called func, and a box to provide what they think would be the function's return value. The fib-like implementation would have been one of the 3 framings that we just saw. Regardless of the framing, however, participants would have had 3 minutes to work on the problem. Okay, now that we've covered our experimental design and stimuli, we'll now turn to our participant recruitment strategy and study population demographics. Our population consisted of University of Michigan undergraduates who had completed or were currently enrolled in a computer science course in the last couple of semesters. 306 students clicked on the study link, of which 57% completed the survey. Of those, 162 final participants passed our quality control threshold, where we checked for participants who rushed through the study faster than 2 standard deviations below the mean. As our population was University of Michigan computer science undergraduates, Michigan's computer science curriculum is relevant for contextualizing our results. Specifically, Michigan's computer science curriculum is taught, at least initially, in C++. Iteration is covered in CS1, and recursion is taught at the end of CS1 and the beginning of CS2. While some non-imperative languages are introduced in upper-level electives, the majority of students do not have significant functional programming experience. Out of our final 162 participants, 91% identified as either Asian or Caucasian. Regarding gender, 70% of participants were men compared to 27% who were women. Programming experience ranged from 0 to 10 years, with half of participants having under 2 years of experience. So now that I've covered our design and recruitment, it's now time for the exciting bit. What did we find? So overall, we organized our analysis around 3 research questions. First, we looked at our 6 stimuli with multiple framings, and we investigated if the framing of a function as iterative or recursive significantly affected the student performance. Second, We looked beyond participant correctness and investigated common errors. We were interested in if the most common student errors differed depending on the framing, and if so, were there any themes to these differences? Finally, we investigated correlations between common demographics and background features such as experience, gender, and spatial reasoning ability with programming performance. So let's look at our first research question. We first investigated student performance by problem version. The chart contains a percent of correct responses for each function framing, and the highlighted cells indicate that version of stimuli had a significantly higher performance than the others, with p less than 0.05. Out of our 6 stimuli with multiple framing versions, we found that 3 had framing-based performance differences. For digit and GCD, students performed significantly better on the iterative framing, while for palindrome, students performed significantly better on the recursive version. For digit, the performance on the iterative framing was better than the performance on both the recursive and tail recursive framings. We observed no significant differences for fib-like, reverse, or triangle. Now that we have covered our overall results, let's look a little more closely at the problems with significant differences. The 2 problems with higher performance on the iterative framing were digit and GCD. As a reminder, digit calculates the sum of an input's digits, and GCD calculates the greatest common divisor of the 2 inputs. We observed that digit and GCD are the only 2 stimuli that output a single number with non-branching numeric computation. The other stimuli that outputs a single number, such as fib-like, have branching computation. As for the case when the recursive framing had the highest performance, palindrome is one of 2 stimuli that involved arrays, and palindrome was also the only stimuli with a symmetric array. Our finding that students perform significantly better on palindrome supports previous work proposing that recursion might be more natural for students completing list manipulation tasks. So in summary, for research question 1, we found that performance was significantly better for 2 out of 6 iterative versions and better for 1 out of 6 recursive versions with p less than 0.05. We also found that better performance on the iterative versions was associated with non-branching numeric computation. Now, since these results are a bit mixed depending on which programming tasks we're looking at, sometimes recursion is better, sometimes iteration is better, we're now going to dive a little bit more into a more holistic approach about common student errors. So we also, when we were analyzing these errors, our main question was if these common errors differed based off the program framing, and we found that the answer is yes. Specifically, we found that students were much more likely to produce wrong answers with incorrect types or structures for recursive and tail recursive program framings than they were for iterative framings. To help make this finding a bit clearer, let's look at a couple of examples. So first, let's take a look at our old friend fib-like. As a reminder, fib-like is a Fibonacci-like function with branching computation. The correct answer for the fib-like prompt was -1. And despite finding no overall significant differences in performance by framing for this particular stimuli, we do observe differences in the most common wrong answers. So for the iterative framing, we found that about 18% of answers gave -3. And this was likely the result of an off by 1 error caused by doing the fib-like loop one more time than necessary. For recursive, on the other hand, the most common wrong answer was 0. In fact, -3 was never given as a wrong answer. While the reasons for this are less clear, it may be that students incorrectly assume that as the base case was always 0, the final result was also 0. Now, while these 2 answers are different, both of these wrong answers are of the same type and structure as the correct answer. However, for the tail recursive framing, things got a bit more interesting. Specifically, for the tail recursive framing, we found that the most common wrong answer was actually a family of responses that were structured as a list and started with the numbers 3, 2. Often it looked like students were giving a list of results or inputs to each of the recursive calls rather than collapsing them into one final result. Regardless, these responses are structurally different than the correct response. In fact, we, in general, found an overrepresentation of these structural differences in the most common errors for recursive and tail recursive framings compared to in iterative framings. Let's take a look at a couple more instances of this pattern. So here we have GCD, and we see the same pattern. The correct answer was the standard integer, and for the iterative framing, the person gave an integer even for the most common wrong answer. However, for the recursive framing, we again see that the most common error was a family of errors structured as lists or tuples starting with, in this case, 70. Now, as a second example, or third example here, the structural pattern is not reserved only to functions that deal with standard integers. We see the same pattern with palindrome, where the correct answer is a Boolean, but the most common recursive framing error is structured as a nested list. While more research is needed, this pattern of structural rather than solely numeric errors in recursive and tail recursive problems may indicate that while students are successfully mentally tracing through the recursive process, they are struggling with collapsing the process into a single answer. So for research question 2, in summary, we found that, yes, common students' mistakes do indeed differ by problem framing. Specifically, students were much more likely to produce wrong answers with incorrect types and structures for recursive and tail recursive problem versions. Now, for research question 3, we finally examine how performance on recursive and iterative problems correlated with demographic and background features. Perhaps unsurprisingly, we found that programming experience or expertise was the strongest prediction of success, with a median correlation of 0.68. Medium, I should say. While we observed no other medium to strong correlations, we did observe several small significant correlations that had R greater than 0.2. For example, we find on average that men perform better than women. We also find that spatial reasoning ability positively correlated with overall performance, while affluence did not. All of the significant correlations are highlighted on the chart in the slide. These findings align with previous work reporting that women students often enter computing programs with lower spatial ability and/or less computing experience. We note that both of these tend to be factors relating to incoming preparation rather than essential differences. Finally, we note that we did not find any significant differences between features that correlate with iterative performance and features that correlate with recursive performance. So as a summary for research question 3, we found that experience, spatial skills, gender, and ethnicity, but not socioeconomic status, were significant features for predicting performance. And in general, we found that the same features were predictive of iterative, recursive, and overall programming. So in summary, in this talk today, we presented the results of a human study comparing performance of iterative and recursive function framings of 6 different programming problems. We shared an analysis of how high-level program features correlated with framing-based performance, an investigation of the most common student errors, and an analysis of correlations between performance and common demographic features. As a result, we covered a number of analyses in this human study in this talk, and it was as this human study is a bit larger than scope than some of the previous work, I want to try and boil our results down to one take-home message. Namely, while we did not find large trends in performance differences between problem framings, we did find large differences in the types of mistakes students make. And that is quite relevant for classes. If you teach both or give students a choice, you may want to make sure that you prepare twice as many worked examples, FAQs, or answer keys, since students are using one framing are likely to show their misunderstandings in a very different way than students who use other framings. Pre-planning for multiple failure models may also help students avoid the perception that they are making unique mistakes, and this may make it easier to identify how close students are to success and what help they need. While much more research remains to be done regarding iteration and recursive problem framings for computer science, and while many of our results are nuanced, this study does give some concrete information about which factors may be more or less relevant to student performance. Thank you for listening to my talk today, and if you would like to learn more about our work or see our replication package, it is available on the project website where there's a link to it on the slide. Thank you.